Your final year project is gone, and the deadline is 48 hours away. Your laptop is acting strange, and the IT help desk is closed for the weekend. As computing students, we don't panic. We use industry-standard tools to investigate and recover the data. Before we touch the data, we must follow the cardinal rule of forensics: do no harm. Every second that laptop stays on, it overwrites potential evidence. We have to maintain strict isolation between the compromised evidence system and our clean analysis machine. We extract data using a free utility called FTK Imager. This tool creates a bit-for-bit physical image of the hard drive and a snapshot of the RAM. We capture the volatile memory because malicious processes often exist only in RAM and disappear the moment the system is powered down. We save this data in the expert witness format, or E01. During the transfer, FTK Imager calculates a cryptographic hash. By comparing the MD5 or SHA1 hash of our image file to the source data, we mathematically verify that the copy is a perfect, untampered replica. This verification is the cornerstone of the investigation. If the hashes don't match, the evidence is unreliable, and any subsequent analysis will be flawed. Now we need to look inside that image. This is Autopsy, a graphical platform that uses ingest modules to automatically analyze persistent storage. These modules work like a team of specialists, indexing browser history, file metadata, and deleted space simultaneously. By running a keyword search for the thesis title, we find a hit inside the recycle bin. The metadata shows a modification date from 2 days ago, exactly when the student said the file vanished. However, this is an older version of the document, not the final draft. Autopsy's timeline feature reveals the sequence of events. Seconds after the student saved their work, a new file appeared, a PowerShell script called updater.ps1. Immediately after the script was created, the system recorded the deletion of both the thesis and the script itself. Correlating this timeline with web artifacts reveals the entry point. Shortly before the script appeared, the student downloaded an executable file disguised as a free textbook downloader. While the hard drive shows us the results of the attack, it doesn't show the execution details. To see how the script actually operated, we have to move into memory forensics. We pivot to the command line to use volatility. This framework parses the RAM dump to show us exactly which processes were running and how they interacted in real time. We use the Windows.info plugin to baseline the OS and Windows.pstree to map the hierarchy of running programs. We find the Trojan executable, and nested directly underneath it, the active PowerShell process. The Windows.cmdll plugin reveals the script's true function. It executed a copy item command, duplicating the thesis into a hidden archive named backup.zip, before wiping the original file from the Documents folder. To find where the data went, we use Windows.netscan. The output shows the Trojan established an active network connection to an external server at the IP address 198.51.100.55. Use your prerequisite networking knowledge for this step. Pause the video and determine the Wireshark display filter syntax to isolate traffic for that IP address. These commands extracted from RAM reveal a deliberate exfiltration event. The attacker moved the data to a hidden location for theft before destroying the original evidence. In Wireshark, we apply the filter ip.address == 198.51.100.55. This isolates the communication between the student's laptop and the command and control server, stripping away thousands of irrelevant packets. We see an HTTP post request containing the backup.zip archive. The server responds with an OK message, confirming the upload was successful. This confirmation timestamp perfectly aligns with the moment the script deleted the local file. In a live incident, you may not have time for a full disk image. When speed is the priority, we use CAPE. This tool is designed for rapid triage, allowing us to collect and parse forensic artifacts in minutes. CAPE skips bulk user data and targets high-value artifacts like the master file table, registry hives, and event logs. This provides immediate intelligence for containing a threat when every second counts. While triage tools like CAPE provide a fast snapshot of a compromise, they are a supplement to, rather than a replacement for, full forensic imaging. These forensic principles scale across different environments. You can apply similar workflows to mobile devices using the Mobile Verification Toolkit, or use ESIF analysis to extract metadata from digital photos for open-source intelligence. The most important tool is your mindset. Focus on defining the normal baseline of a system so you can identify deviations. Every piece of digital evidence is a breadcrumb that helps you reconstruct the truth. To build these skills safely, use the SANS SIFT Workstation. You've now seen the full pipeline: acquiring images with FTK, analyzing disks in Autopsy, parsing RAM with volatility, tracking network theft in Wireshark, and conducting rapid triage with CAPE. Stay curious and happy hunting.